So a warm welcome to everybody and a huge thank you to our webinar host today, John Roth. He is going to wow us with an amazing presentation based on rock stories around South Africa. To all of our teachers that are enjoying their holiday, I am jealous. We are back for a few days now and we are looking forward to the next holiday. But just to wish all of our third term schools a wonderful break and hopefully that you enjoy some time off and get ready for the next term. Before we start today, just a reminder to please make sure that you join SAGTA and that you pay up your membership for the year. It is a wonderful opportunity now, especially before examinations, where you will have access to the SAGTA topographical map downloader, and you can create all of your own maps for your examinations, as well as it's the perfect opportunity now to submit something to PrepShare so that you are able to also have access to some of other teachers around their country's amazing resources, as well as some of their assessments. We are also calling for teachers to submit abstracts, or if you would like to join the IGU CGE conference in Stellenbosch, when we send out the link for today's webinar, I will share more info with regards to that webinar, regards to that conference. So yeah, just a few admin things. We will today have a Q&A session once John is finished. And this will be a great opportunity for you to ask him any questions that you have around rocks or anything that you have been wondering about. But before we begin today, I'm just going to hand over to Bridget, and she has got some important information to share. Bridget?
Thanks, Kirsty Lee. And I just want to share, and also so good, John Bristow is also resides in Hermanus. And John, now the conference that Kirsty Lee was referring to, the IGU CGE, to be hosted in Stellenbosch, we have also included a wonderful field trip excursion on that. And John Bristow is going to hopefully, with his team, be the geologist to go and visit the geological trail, which will be fantastic. And this is the association that is very much involved in it. So it is a core group of geography teachers. So hopefully many of us will be able to meet you. Well, I mean, you know me, but others will be able to meet you in the flesh, because that is an amazing display at the Harold Porter. And thank you very much for that, an amazing resource. But what I want to quickly discuss is we've just come from a wonderful meeting, not to be a spoiler alert, but please, if any of you have got a prep school or a primary school linked to your school or your own children in primary school, please can you encourage their social sciences teachers and foundation phase teachers to join SAGTA, because a new addition to the map downloader is going to be 2 new projects. So for SAGTA members, you'll know that you can access the topographic maps and the orthophoto maps and the hybrid map layers. The 2 new projects, drum roll, is going to be a lovely global map data set with a variety of thematic maps that you usually find in atlases, which will be very pertinent for the intermediate phase teachers and GET phase teachers as well, plus another set of wonderful data sets which you can use for South Africa, so that when you teach, you'll be able to have updated information on population statistics, geological layers, a beautiful geological map, thank you, of South Africa. And we want to encourage all budding geologists to join SAGTA. You don't have to be a geography teacher, because mapping is also a key part of your game. And by being a SAGTA member, not only are you supporting budding earth scientists, but you also helping us provide mapping resources for this community. So please, please pay your subs. This is how we develop these projects. So I want to please spread the word. Please join SAGTA. Thank you, Kirsty. Over to you, John.
Thank you very much, Bridget. John, while I'm busy introducing you, you are welcome to share your screen so that we can start today's webinar. So John Roth, we welcome you today. He is a specialist nature and geology guide and trainer, helping curious people discover and learn more about South Africa's exceptional natural and geological heritage. He has spent his professional life sharing the wonders of nature with people of all ages, from WESA school programs in the early 1990s, the Botanical Gardens, Hilton College, and many other schools. And I'm so excited that we will also have him on one of our excursions now in the next 3 weeks in the Mpumalanga area. To his current work, he is a specialist guide and trainer with a focus on the interconnections between geology, ecology, and people's daily lives. He joins tour groups, leads walks, and visits schools, lodges, and reserves, helping students, guests, and guides understand the remarkable rocks and landscapes of the region. And we will share his information at the end. We'll put his email address if you're interested. And we're also actually looking at doing a hike in the Walter Basuli Gardens in the coming months when John is up in Johannesburg. So if anyone would like to join us, we'll send more information out about that. So a huge warm welcome, John. And yeah, over to you.
Thank you very much. Kirsty, I wanted to start with just something quite personal. There's several people who are participating in this webinar who've really mentored and supported me on this journey of growing into geological guiding. And some of you I've known for decades. Pam, I particularly wanted to acknowledge you as a supportive friend and colleague. John Bristow, your geological expertise has really helped me greatly. And I wanted to acknowledge all of you as educators. I know that teaching is hard work. I worked in a private school for many years, and I know any school, your time is precious. And so thanks for making the time to participate in this webinar. I hope to give you something inspiring and help you connect with the marvelous rocks and landscapes of our country. So I am a guide. I'm a nature guide, and I've started specializing in geology probably in the last 6 or 7 years. And I found people are fascinated and often struggle to find ways to connect with and understand rocks. So I'm constantly looking for ways to make rocks more interesting. So I thought I would start with a banana. Here we are. Now, this particular banana, Kirsty, you'll be pleased to hear this. This is grown at Umbaba Estates, Hazy View. And we will be there in a few weeks' time with your students. So here's a banana. Now, bananas are high in potassium. And so because I have a kind of big picture way of thinking about the world, well, I brought the world along. Here's Africa. Just notice that the world is also quite soft and squashy and pliable. That's going to help us a bit later on as we make sense of some of the rocks I'm showing you. So roughly here is where that banana came from. So I had a quick look on a geological map, and it turns out that the rock type where that banana was grown is granite. So I brought along some granite. And this particular piece of granite came from KwaZulu-Natal, not from Mpumalanga, but it's got a certain mixture of minerals in it. Let's hold that a little bit closer. I don't know if you can see some big pink crystals. Yeah, there we go. There's one. So that's a certain kind of, there's a mineral called feldspar. Some of you are probably very familiar with this. Some of you may have forgotten. So one of the ingredients of granite is feldspar, and there's a particular kind of feldspar with lots of potassium in it. So this banana got its potassium from the soil, and the soil got its potassium from the granite. So just making a little connection there between rocks and our daily lives. So what I wanted to do is to share with you a few pictures, and I'll probably move back and forth between the screen that's showing me, because I've got these rocks at hand, and I've got pictures of the rocks on the screen, and we'll just see how that unfolds. So I'll just, let's get sharing the screen so long. And there there's a variety of images. This is in the Waterberg. I was there just a few weeks ago. So, I mean, when we're looking at rocks, we're very much looking at landscapes and the way that rock types influence those landscapes. This part of the Waterberg is sedimentary rocks, so various kinds of sandstones and mudstones. And then I always like to get close in with the details. So this is a little piece of sedimentary rock, very hard, and it's been used as a stone tool. So in my experience, especially when working with school groups, one is always looking for the human connection. You know, a rock is not particularly inspiring to your average teenager, in my experience, unless it connects with their lives in some way. So this sedimentary rock, you can see the lines there, is quite hard, and it's been changed by people. It's had some flakes knocked off it, and these sharp edges, this is probably a middle Stone Age tool, and these edges would have been sort of further chipped by people to maintain a sharp working edge. A little glimpse of some of the sandstones of the Waterberg. I'm not going to go into too much detail on those now. And then a really significant rock for us in South Africa. And without this, we wouldn't be able to watch this presentation, because this is a piece of banded iron formation, and it's very, very high in iron-rich minerals. And rock like this is mined extensively in South Africa. And so if there's any piece of steel or iron in the computer or phone or tablet through which you are experiencing this image right now, then it's probably got its origins in banded iron formation. So we can give a vote of thanks to that particular type of rock. And then I wanted to go a little step backwards. What I'm trying to do here is to take rocks and connect them to our lives and connect them to places as well in South Africa. In my experience, there's too much information coming at us, whether it's young people in school or older people like ourselves. There really is a lot of information coming at us every day. And an antidote to the information overload is to be able to hold something tangible that tells a story. So these are actual rocks that I have in my actual house, and one can hold them, feel the weight of them. And I do just encourage you when teaching this to students that whenever possible, that you put a physical rock in their hand. That's if you can't go on a field trip. Obviously, a field trip plus a physical rock in the hand is even better. But at least in the classroom, a physical rock in the hand is going to connect more powerfully with the students. So this rock has got some rounded structures on it. Kirsty, if I move my cursor like that, is it moving on your screen as well?
Yes, we can see it. Yes.
Great, thanks very much. I'm assuming my voice is coming across clearly.
Yeah, you are perfect.
Great, thank you. So this piece of rock comes from the Abel Erasmus Pass. When one drives from the Lowveld, the town of Hoedspruit, then you drive through a set of tunnels and you climb up a very steep escarpment, and you're heading inland back towards Johannesburg, and you go up the Abel Erasmus Pass, and there's a whole long section of road where you're driving past this type of rock, which is so very high in limestone. This is probably dolomite. So these are very, very high in calcium, these rocks. And they're very old. In terms of Earth's history, they're more than half the age of the Earth, really. And this is from a time in Earth's history when oxygen was first being produced in large quantities for the first time. So what we're looking at here are actually a type of fossil. These layers, these rounded domes, are something that we call stromatolites. And they are layers, and there's still a few of them living today. Shark Bay in Australia is one of the few places where they still occur. So it's a layer of blue-green algae, and they're in a shallow sea. I'm taking us back into the past now. So those mountains that we drive along and see these things on the side of the road, that was once layers of sediment being deposited in an ancient sea. And this rock tells all of those stories. But back to what we can actually see in front of us, these layers are calcium left behind, and that calcium came out of the seawater that these organisms were living in. And as they're living and photosynthesizing, and at this stage in Earth's history, this is it in terms of life forms. You get some big stromatolites, a couple of meters across, but there weren't any trees, there weren't any animals walking around. There was no oxygen in the atmosphere. And over a very long period of Earth's history, these single-celled organisms were producing oxygen in large quantities for the first time. And when that oxygen gets into the sea, into the seawater, it binds with iron, which at that stage is thought to have been floating, for want of a better word, in the seawater. And oxygen and iron binding together make a heavy molecule, which then sinks to the bottom of the sea. So let's go back to the banded iron formation. This is a piece lying in my garden, and it's sitting vertically. So in your mind, you can turn this thing horizontally, and these are layers, fine layers of iron-rich sediment deposited in an ancient sea. And that meant that oxygen was going into the atmosphere, well, into the sea first, and then as the sea got full of oxygen and saturated, I suppose, then there's plenty of oxygen going into the atmosphere. So that's a time in Earth's history when oxygen gets into the atmosphere and life as we know it on land could really get started. So we owe something of a debt of gratitude to these little creatures. Okay, I'm moving around quite a bit to different times in Earth's history. I'm not going to go into detail about dates and times and millions and billions of years, because I find that can be a bit overwhelming. But I want to try to speak to the immediacy of the rocks that we're seeing in front of us. So here is a piece of rock from Sea Point in Cape Town. Very, very significant place, because it's a place where you have the first rock to be there, if you like, were sedimentary rocks, certain types of shales, and those rocks were intruded by granite moving into them. And whenever you have a meeting like that, and that meeting is going to be happening kilometers below the surface, very, very high temperatures, completely different to the kind of environment we have today, it's quite a dramatic and chaotic situation. So what we've got here, I'll go in a bit. Earlier, I showed you a piece of granite, and it had crystals of feldspar in it. Those were pink. These are also crystals of feldspar, but they're a creamy color because it's a different kind of feldspar. And in this case, the granite intruding the shales would have melted the shales. There's great heat, there's great pressure, there's water in those shales. So you have quite an explosive environment. That water gets superheated well beyond 100 degrees Celsius, but it can't boil because it doesn't have anywhere to go because it's surrounded by rock. So it really causes quite a mess. And part of that mess is going to involve pieces of the granite getting separated out of other pieces of the granite and moving about a bit, and then being surrounded by this dark liquid, which is probably the melted shale. So a real mixture. If you're in Cape Town as an educator and you can get to what's called the Sea Point Contact, there are rocks like this there, and I highly recommend a visit to that place. So I guess what I'm also doing as I'm sharing these different stories is I'm speaking about a range of geological processes. And I always find that students, or anyone really, responds to a story about a rock rather than just the rock itself. And the processes are part of the stories of these rocks. So I like to include those in any narrative. There's that chunk of granite that I showed you earlier. This comes from the granite basement here in this part of KwaZulu-Natal where I live. And the basement really means that they're like the foundation of a house. They're at the bottom and other rocks sit on top of them and get built on top of them and move about on top of them over time. This is quite unusual granite in that you have these very big crystals. Granite usually has smaller crystals. The size of the crystals is to do with the amount of time that it took this particular type of granite to cool. This would have cooled down very, very slowly. Again, deep, deep down, this granite would have formed maybe 10 or 20 kilometers below the surface, and a long time ago. Yes, so this is a very significant rock, and it's a chunk of dolerite. And you don't have to remember these names, because there might be a few unfamiliar names. And I do want you to remember, perhaps more than the name, the fact that this is showing us something quite key about rocks and the role they play in our lives. So in the center of this chunk of dolerite, we've got fresh dolerite. So I cracked this piece in half. So it was exposed for the first time since it was formed. And just to give a date to this dolerite is part of the breakup process of Gondwana. So Gondwana, that most recent supercontinent that Southern Africa and Australia, Antarctica, India have all broken away from. And part of that breakup process involved huge quantities of magma coming up through the earth, pouring out onto the surface. The magma that didn't make it to the surface cools down in place under the surface, and so it cools down a bit more slowly than the magma that poured out onto the surface, which is basalt. So this is dolerite. So this dolerite is quite high in iron, and what looks like an almost painted coating on the outside of this dolerite is simply dolerite that is weathering. So it's breaking down, and the heavier minerals in this dolerite have started to weather away, and we're left with this quite light, quite friable, it breaks down easily, sort of powdery coating. And this gives rise to clay soils. So let's now go to the Karoo. We're driving through the Karoo from Johannesburg to Cape Town, and we're seeing quite a lot of flat-topped hills. Many of those flat-topped hills are made of dolerite, and those dolerite rocks are going to give rise to clay soils. So we'd expect to find some clay soils in that area. Pietermaritzburg, Hilton, an area where I live and spend a lot of time, we've got lots of dolerite, lots of red clay soils. And obviously the soil type determines what you can grow in it. And that has a huge influence on our lives in South Africa, because it determines what crops grow where, how much crops cost to transport. So if a particular crop can only grow in a certain kind of soil, then it's going to cost a certain amount to transport it to another part of the country. So again, what I'm trying to do, Kirsty, perhaps for your benefit here, because you're interested in urban geography, is to show the links between the rocks, the soils, the economic effect that the rocks and soils have on our daily lives and the way they intersect. Okay, on to a completely different type of rock, really significant. We're now going back in time to when long before Gondwana broke up. But this tells us, this rock type, and the fact that it's got chunks of other rock in it, this tells us that at one point, South Africa was over the South Pole, because this type of rock is formed by glacial melting. So glaciers grind over huge portions of the Earth's surface, and as they grind, so billions of tons of ice are grinding and crushing rock into a fine rock powder, if you like. That's this stuff here. And they're also breaking and crushing and smashing various different kinds of rock that they travel over. So there's a chunk of something, not quite sure what. Here's a bit of quartz. This looks like a bit of sandstone. All of these things would have been ground up and crushed and been underneath the glacier. So when that glacier melts and everything that was underneath the glacier pours out into lakes and streams and rivers, you've got a mass of different kinds of material falling and settling into this rock powder. And over time, that consolidates and becomes stone, a glacially derived rock type called tillite. So tillite, if you think of tilling a field, glaciers till the Earth's surface. So tillite, that might be a way to remember it. Right. Now this is a great one to put in front of a child who's not interested in rocks, and then just throw out the question. I'm a great fan of inquiry-based learning, by the way, that the idea that people learn through engaging with a question, and pop this in front of a child, and again, the physical item is best, and just throw out the question, how do you think rocks bend? Just to save a bit of time here, I'll explain this. But what we've got here is, remember I showed you a piece of granite earlier. So if we take a piece of granite and we subject it to great heat and pressure, then it actually starts to change. And great heat and pressure happens at depth. So rocks like this are formed very far below the surface, often where plates, so with our understanding of plate tectonics, plates push against each other. Some plates go underneath other plates. There's a great deal of pushing and mashing and squashing and heating. And so granite would start to separate out into its different components. And you might have a few other bits of different kinds of rock mixed in there as well. And as those components start to melt but don't melt completely, they're soft and they start to separate out into bands according to their melting points. And what we've got here, these bands of dark minerals and then light minerals, are places where those original minerals that made up the granite and a few other rocks started to separate out. And at those depths and at those temperatures, rock is plastic. It's very much very, very different to our concept of rock that we know on the surface. Rock is plastic, it's soft, it's malleable. I like to think about the stripes in Aquafresh toothpaste. If you give that a good squeeze, and then if you can imagine yourself now, you're about to brush your teeth, but you get distracted by thinking about geology. And so you squeeze that Aquafresh toothpaste into the basin and just move it around a bit. And yeah, you're kind of playing the creator there, moving those minerals around in their soft state. And it would be something like that, the formation environment of this rock, which is now a different kind of rock because it's granite that's been changed by heat and pressure. And we call this gneiss, so Gneiss. And so this is a metamorphic rock, and it is a rock that forms the basement in many parts of our country. And there's different ages of these granite and gneiss basement rocks, but they form the solid and very stable foundation for much of the world, really. Let's move on. Oh, yes. So here, now, at this point, perhaps the children in your class are saying, well, that's all very well, but what's it got to do with me? So at this point, I might turn the classroom light off, or even better, to get their attention, one might turn off all technology and point out that the electricity we are enjoying, which runs all these devices which we need in our lives, that electricity in South Africa is primarily being generated by coal. So this is a chunk of coal, and it's quite light. And it's interesting for children to hold a chunk of coal in their hands because they're often surprised by how light it is. And once you're holding that thing in your hand, for you as an educator to be able to say you are actually holding a piece of ancient swamp that became a rock over time, there's a bit of power in that statement. Not only electrical power from the coal, but the power to be able to get a child to imagine that this thing that they're holding in their hand has actually got energy in it from ancient sunlight that can power their cell phone. And that's a sure way to get a child's attention, is power or otherwise to a cell phone. Right, so here, now where's the other one? Yes, one of these two is gold. Not that one. So this one or this one is gold. And one of them is fool's gold. So if you were a prospector and got it wrong, you might have just lost yourself or gained yourself a fortune. Gold is always a winner. People are interested in gold. You know, and the fact that Johannesburg is where it is because of gold. And you know, the name of the city, Egoli. And gold is a powerful. It's a powerful symbol in South Africa, apart from being a significant rock or mineral. So what we're looking at here, this one, is fool's gold. So it's iron pyrite with a bit of copper mixed in. Actually, this came from Phalaborwa, a very significant mine at Phalaborwa, by the way. And so you've got this, so chemically it's got iron, copper, and sulfur in it, I think. Correct me if I'm wrong, Mr. Bristow. And this darker coppery looking part is, it's a section of the pyrite that was exposed to the air for a long time. And this more golden looking part is a section. So there's a big mine dump at Phalaborwa. I climbed up there, knocked some chips off a few rocks. So I got some fresh surfaces. This is the fresh surface of that pyrite. So it's got a very golden look about it. That's got a deeper coppery kind of look. And this here is real gold. This is from the reefs in Johannesburg, and this is actual gold mineralization in place. This is something that catches lots of people's attention, and I get asked about regularly. I've shifted now from gold and pyrite and mining, and what I'm holding here in my fingers is a piece of shale. So shale is a rock that was mud. It's a sedimentary rock. You have mud building up in layers in an ancient sea or lake, estuary, something like that. And over time, that becomes rock. These features look like fossils, but are not. If you can imagine, so you've got a whole lot of layers of mud settling and becoming stone. What that means is that you have very, very, very fine spaces between those layers, weaknesses, if you like. And water can do extraordinary things. Rock is much more permeable than we think. And water can easily travel long after the rock has been formed, water can travel through a rock along lines of weakness. So water traveled along this face. Maybe it traveled from here and went this way. Maybe it traveled here and went this way. But as it was traveling, the water was carrying certain minerals in solution. This looks like manganese. And so the water gets in between the layers in the shale, deposits some manganese, and so it's depositing the manganese as it recedes. So if you can imagine a block of shale, quite deep in the ground, but it's got some water around it. During wet years, that water is going to find its way into the shale and carry the manganese with it. During drought periods, maybe you have a few hundred years of a dry cycle, then that water is going to recede and it's going to leave behind these mineral traces. So these structures we call dendrites. Dendron referring to something that looks like a tree. So these features often look like trees. There, what have we got? Yes. So something that often interests people is how do you get bubbles in a rock and how do they fill with something? Because as I said earlier, we have this idea that rock is hard and difficult to get through, but rock is very permeable in the right conditions. So this is a chunk of basalt that I'm holding. Basalt is a really significant rock in South Africa. And as I said earlier, when Gondwana was breaking up, huge quantities of basalt pouring out over the surface. Many of those have now been eroded away, those basalt layers, but many parts of the country where there's great basalt to see. The KwaZulu-Natal Drakensberg is an example, and Eastern Kruger National Park another. So this chunk of basalt, when it poured out onto the surface as lava, it would have had gas bubbles in it. And those gas bubbles then fill with, remember I spoke about water traveling through rock, carrying minerals dissolved. So water would have traveled through this basalt after it was formed, and it would have deposited minerals that it was transporting into these spaces. So these little crystals that fill up the gaps, and crystals always interest children. They usually want to know how much money they can get for selling them, but it's a starting point. And you can then explain this interesting process. And so I guess I'm always looking for bridges. So we start with crystals, ooh, bling, shiny, exciting. And then we transition from that into, well, how does a crystal get inside a dark rock? And then we can tell that story. Yes, something different, a piece of rose quartz that has been sanded by the wind. So this came from the Namib Desert. And that smooth surface that you can see shining there is because it has been sandblasted literally by billions of grains of quartz sand blowing over it in particular directions for thousands and thousands of years. Again, quite nice to hold it and imagine the force of that. Yeah, it's like Aeolian sandpaper, you could think of it. And another significant force in our country in terms of erosion, using the idea of sandpaper, is rivers carrying quartz grains, and they act like liquid sandpaper and grind away. So again, always looking for ways to link things that we are familiar with to processes on the earth. And then what else have we got? Yeah, a couple more. This is a stone tool, Middle Stone Age. Yeah, I'm not quite sure what it would have been used for, but this came from the Karoo. It was lying on the side of the road. Normally one doesn't pick these up, but it was completely out of context. And you can see this structure here. It's called the bulb of percussion. It means somebody hit it over there a really long time ago, maybe 100,000 years ago, knocked it off a bigger piece of rock, possibly dolerite, can't quite tell from here, and made a tool out of it. So there's a link to our lives over time in Southern Africa. And then this is just another piece of banded iron formation, but it's got a slightly different look to it. There's lots and lots of this stuff in the country. And then that's magnetite, but I'm going to explain that to you visually. And I think I'm going to do that now. So I'll stop sharing and see if we can get back to, yeah, there we go. So here's a chunk of magnetite. And here's my torch, and it's got a magnet on the end. So, there we go. I don't know if you heard that. Oh, it's quite hit. So there really is a lot of iron in this rock, and it's magnetic. So kids respond incredibly well to that. Well, so the adults, actually. I bet you're enjoying this. There we go. So before we move to questions, I wanted to just share with you one of the techniques that I found very effective in getting kids to conceptualize some of the big picture processes we talk about. Kirsty, I know in particular, found this useful. So this is a gym ball, 75 centimeters, I think, and this is a tectonic plate, and it moves over the surface. Yes, Ponjol, magnetite. Yeah, so magnetite could probably form in different ways. That piece of magnetite came from a mine at Phalaborwa, and the origin of those rocks at Phalaborwa is primarily igneous, so material that came up from deep below, a volcanic event, and it also changed the rock that it traveled through. But the magnetite would probably have come up from below, so you could call it igneous. So here's a tectonic plate, and here's another one, and they move over the surface of the earth. The idea that an ocean can be on a plate is quite challenging to explain to many learners. So I've got a blue plate, and then I'll stick a continent on top of it, and the whole lot can move as a plate. And then here's another plate. And so we could have subduction. This plate goes underneath this plate. We could have the plates, and you can tear them up into pieces and do whatever you like with them. But it works quite effectively because the children can see these things moving. Because otherwise, plate tectonics is really a very abstract concept. So I might cut along here and make the San Andreas Fault, and then we could push those plates against each other. We could do some mountain building. Let's make the Himalayas. There we go. Yeah, we might have an earthquake, actually. That's quite topical at the moment. So the one thing I learned is that the scale here, with a ball of 75 centimeters diameter, this is roughly to scale. This is how thick the crust is, the thickness of this plate. It's about a millimeter, a bit less. So, Earth's crust maximum thickness about 70 kilometers compared to the full size of the Earth. So there's a tool that you might find useful. And I think it's probably time for some questions. So go for it if you've got any questions.
If there's anybody who would like to ask any questions, you're welcome to either type them in the message bar, or you're welcome to turn on your microphone and then ask John questions during this time.
John, maybe I can just get the process going and just, yeah, well done. I mean, your simplification of processes is wonderful. And you and I are fortunate, and I think many of the kids that we've been involved with, we can get them out of the classroom and take them to see real rocks. One of the great ways I found in trying to teach youngsters about geology and minerals and our reliance on those minerals is in the classroom or in your office where you're sitting now, and just to point out to people that about 90% of the building that you're in actually comes out from the ground or underneath your feet. In other words, it's all about the rocks and the geology. So if you look at the brick and mortar, it's all holding up the building. If you look at the steel reinforcement, it's stuff that you can point out and see. One of the scarcest commodities, but most important commodities today, are aluminium and glass. Good old silica sand, which we tend to discount as not being important. I see you didn't even bring it up today. Silica is extremely important and increasingly scarce. And many countries now are actually recovering, pumping silica sand out of the oceans. And that has huge environmental consequences as well. But if you look at all our modern cities and the school classroom you're sitting in, the amount of plate glass is immense. And we should be finding ways to reprocess a lot of the building material. In fact, in the UK, when you demolish a building, you are legally required to process the brick and mortar. We throw away glass and glass bottles and wine bottles into the landfill. It's an immense waste. And I don't know if people realize how important clays are. Again, they're not sexy. We don't really go looking for them. But just think of your ceiling and classroom walls when they painted. Why does the paint actually stick, upside down on the ceiling? Well, there's a wonderful clay called adipulgite, which you'll find in most, most paints, and that's the clay that sort of gives the stickiness such that it holds onto the ceiling and onto the walls. So there's a very simple way of making the classroom also come alive geologically. And then obviously the two other ones is the vehicle that gets you to school in the morning. Well, a modern vehicle is full of critical minerals, the batteries, the iron and steel, the aluminium, the glass again, and then the other one obviously is the cell phone. I in fact have some quite neat diagrams in a little, I don't know if it's 5 or 10 page presentation. I can send it to you and Bridget, and it might be something for you to just pass around to your teachers. Buying a book is expensive, but circulating a little presentation is easy these days. Or you can put it onto a PowerPoint or even onto YouTube and use it. It shows a building or a house and all the different minerals that are used in that house. Likewise, a motor car. And obviously the real interesting one is a cell phone. So that's just a few comments to add to your approach of making the stuff so simple and informative.
Thank you. Thanks very much, John. I see we've got a question here. Stephen is asking if I could explain how does weathering of silicate rocks contribute to carbon capture? And that question is chemically a bit beyond me. So John Bristow, I'm going to put you on the spot here. Are you able to answer that question? How does weathering of silicate rocks contribute to carbon capture?
Yeah, we just step through it a bit too. Silicate rocks, by definition, would have a lot of silica in them, SiO2. And the rocks that really give you the best carbon capture for obvious reasons are more typically carbonates. John talked a little bit about carbonates. For example, there's been some extensive work and deep drilling on the Ponderland Flats, Maputo land out east of Southern Africa. And ponderland are those, they're basically marine sediments that were deposited on top of the Lubombo Mountains, and I'm getting a bit technical, but carbonate rocks are very good for carbon capture because obviously they already have some CO2 in them. Basalts aren't too bad because they again tend to be quite porous, and they a classic. John talked a couple of times about the Lesotho lava plateau, kilometers of ancient lavas, 182 million years old. Those rocks have about 50%, 45% silica, and they have in places or are being looked at for carbon capture. Granites don't really work that well because granites are full of, have a very high proportion of silica. So you really want, rocks that are either porous or soft, like carbonate rocks, and they are even cold. Probably one of the most critical types of rock or material for carbon capture is peat, our peat beds, and we here in Southern Africa are destroying those peat beds, and peat beds are something we should do a lot more to conserve it because they are wonderful. They basically material that's starting to form coal, and so it's locking up lots of CO2 in that process. So look after our peat beds, please.
Thanks, John. Any other questions from anyone? Anything that we talked about and looked at today? Any geological questions you might have? Most welcome.
John, just to add another little piece onto your Sea Point contact. People should be reminded of Charles Darwin and the Voyage of the Beagle.
Yes.
And he was, a famous person who did a lot to identify and look at, life forms and how life evolved on this planet of ours, Earth. Anyway, there's a trip underway at the moment. I think it's his niece, and a tall ship is visiting Cape Town as a celebration of his life and what he achieved. I have some information. I'll pass it on to you and Bridget, and if anyone's interested, you could certainly follow up on that, particularly if you live in Cape Town. There are a number of functions, and there's a play about Charles Darwin. I think it might be on the 24th, I stand corrected. And we too, I think it was last year, we did a fairly comprehensive guidebook, and we try to simplify the geology at the same time. We did a guidebook on the geology of the Sea Point contact and the west side of Cape Town, the Atlantic seaboard. And there's some wonderful variety of geology along there. And we did a section on Charles Darwin and his voyages and contribution. And again, we'll happily share it, John and Bridget, and you can distribute it, particularly for educators and teachers in and around Cape Town.
Great, thank you.
I don't see any more questions, so we will end today's webinar now. John, just a huge thank you from everybody at SAGTA for such an amazing presentation. I think it was so fascinating to be able to see the different types of rocks in your presentation and understand where they come from, as well as you've given us quite a few tips on how we can teach some of the rocks in the classroom. And always, I love your bouncy ball with the plate tectonics example. And I'm actually teaching that section in the coming weeks, and I look forward to going to find a bouncy ball. So just a huge thank you very much. And to everybody that has joined today, I will make sure that we can send out the recording of this presentation to everybody, as well as John's contact details, so that you'll be able to contact him for any questions that you might have, or if you want to go on any walking adventures. And we just hope that you had a phenomenal holiday all our third term schools. And to the students or the teachers that have gone back to school, if you're a fourth term school, may the force be with you this term. And we hope that you have a wonderful, successful term, and good luck with your examinations in the coming days. And lastly, again, thank you very much to John and to the other John for your insightful information. Have a wonderful afternoon, everybody.
Thanks.
Thanks. Well done, John.